to introduce the next speaker for this morning, Professor Tatiana Toro from University of Washington at Seattle. Professor Tatiana has a very impressive set of results in her career. She works in geometric measure theory, free boundary problems, potential theory. I told her, and there are a couple of very nice videos of her lectures on the web, like MSRI and many others, which I really encourage you to take a look. I've learned so much from her talks. And so today she will be speaking about this free boundary regularity for almost minimizers. It is a theory very close to my heart. I have been dedicating many of my research time to deal with the theory. I think she has a very nice set of results to tell us about today, and I'm pretty sure you are going to enjoy. Please, Tatiana.
Thank you. Thank you very much for the nice introduction, and thank you very much to the organizers for the invitation. As Yannis said, I have never been to Rio, and I have only been to Brazil point-wise. I have only been in Tabatinga, which I bet most people in the room don't know. It'll be your homework to figure out what it is. Very, very small town in the middle of the Amazon jungle, and that's the only part in Brazil where I have ever been. It has been a pleasure. It's a beautiful city, and it's a very nice place to be here. Okay, so what am I going to talk about? I'm going to talk about free boundary regularity for almost minimizers. So the first thing I'm going to do is I'm going to tell you what on earth is an almost minimizer. In fact, I'm actually going to remind you what minimizers I'm going to be looking at when I look at almost minimizers. And what I should say is that if you remember David Jerrison's talk, what David did is he removed the minimizing aspect and focus on the equation. What I am going to do is I'm going to keep, to some extent, the variational aspect, and as you'll see, the equation will not longer be there. So these are, we look at the same thing, and then we went two completely different ways. And only at the end will I tell you why we're interested in these. In fact, it's because we got stuck many, many years ago in a question that both Eduardo and Diego had asked me when I was working with Manolis Milakis, who was mentioned in the previous talk at the University of Washington. We were very stuck. We didn't manage to do anything. And then, well, then things evolve. In math, it's always like that. OK, so let me tell you what's the corresponding minimizing problem. Oh, before I forget, so this is joint work. Part of all of it with Guy David and part of it with Max Engelstein. Let me advertise Max. Max is a grad student at Chicago currently. He'll be graduating next year. He's a student of Carlos Koenig. OK, so let me first set the minimizers with free boundary. What I do is I take a bounded connected Lifshitz domain. Think of the unit ball. That's more than enough for our purposes. We take two functions, which are in L infinity, and the class of functions we're going to look at. They're L1 log and gradient in L2. And we look at the following minimizing problem, which gives rise to a free boundary. So this is the minimizing problem that was looked at, as all of you know, basically, by Alt-Caffarelli or Alt-Caffarelli and Friedman, depending on the situation. So we look at functions which are in our admissible space, and we look at the gradient squared, q plus, the characteristic of u is positive, plus q minus, the characteristic of where u is negative. And we look at the minimizers of these among all functions in k of omega where the boundary data u0. And the question is, do minimizers exist? How nice are they? How nice is the free boundary? We'll talk about that. I'll remind you what the results are. Just a little bit of terminology, and I'm going to try to package everything in the same thing. But so if we're looking at the case where q minus is identically equal to 0, and u naught is greater or equal to 0, we call this problem the one-phase problem. Okay? Why? Because because then we only have the positive part and the 0 part. I'll draw a picture in a minute. And in the case when Q plus and Q minus are both positive, then we have the two-phase problem. Okay? So as I said, this problem was looked at. Initially, the one phase by Alt and Caffarelli in the 80s, early 80s, Alt-Caffarelli and Friedman a little bit later in the 80s for the two-phase problem. Okay, here is what they prove. I know lots of you know what they prove, but some of you might not. And in any case, I'm reminding everybody, okay, just in case. So they prove that minimizers exist. They prove that, and so if U is a minimizer, so U plus, I remind you, is a positive part, is the maximum of 0 and U. U minus is the maximum of 0 and minus U. So U plus and minus are subharmonic. If I am in the one-phase problem, take U minus to be identically equal to 0. So they're subharmonic, and they are harmonic, and U, which is U plus minus U minus, is harmonic wherever you have a sign. Okay, so maybe it's time for the first picture. So omega is going to be the unit ball. Here is our free boundary, and here we have Laplacian of U is 0, where U is positive. Laplacian of U is 0, where U is negative. They made an assumption that told us that they didn't have pools of zeros. And there's something in between. Okay, what is this? And I know I drew something beautiful because, well, that's life. I'll call this set gamma of U is the thing in between. We'll talk about that set. Okay. What else did they prove? Well, they proved that across this set, U is Lipschitz. Okay? Of course, we're not talking about what happens at the boundary here. We're not going to touch that. All the things I'm going to talk about are interior results. And they also prove that, let's assume, and I always favor Q plus, bad habit. I mean, same thing could be said for Q minus. But what they prove is that if Q plus is bounded away from 0, then not only is U plus Lipschitz, so is not only U plus is controlled above by the distance to the boundary, but is controlled below. Okay? So this is what this is telling you, is that if you take a point here in the positive part, and you look at this point here, the value at the point is comparable to this distance. Okay? Above and below. This is very, very, very important. This tells you the solutions are non-degenerate. We have heard about non-degeneracy. This is key. Okay? What else were they able to prove? They were able to prove that, and if you have never heard this word, don't worry, just ignore it for now. We'll go back to it, maybe, or I'll say a word now. What they were able to prove is that U plus, the positive side, is a set of locally finite perimeters. So this set that I drew here, so this part doesn't matter, but what this tells you is that this boundary here is a rectifiable set. What does it mean to be rectifiable? It means, let me give you several definitions. It means if you're at a point and you blow up, you get a tangent plane, a unique tangent plane. It also means that that this set that I drew there can be written as a countable union of Lipschitz images if I am in Rn of Rn minus 1 and a set of measures 0. Okay, so it's a weak notion of regularity, but it's a very important first start for the problem. Okay, so, and this is it. Namely, well, no, they prove way more, but this is it with respect to the function. You cannot expect any more regularity of the function across. And so the question is, okay, well, especially if you had never heard of it, this sounds like a very weak notion of regularity. I mean, what else can you say? Okay? So let me tell you what else happens? So now we go to the regularity of the free boundary, which is the interesting part. Well, actually, no, both are interesting, you'll see. But so this is the free boundary, the union of the positive, of the boundary of the positive part, union the boundary of the negative part. Okay, and so all of this is for a minimizer. I haven't even told you what an almost minimizer is. I'm going to give you a set of results, and then I will give you the attributions, and I will tell you who proved what and why there's kind of gaps, you know, time-wise in these things. So if Q plus and Q minus are Holder continuous, we always assume that one is bigger than the other, and this one is greater than 0. And we assume that Q plus is bounded below. Then if n is 2, 3, or 4. Let me emphasize, we live just because the numbers are important, in particular if you come from GMT. So if n is 2, 3, and 4, then the free boundary is a C1 beta n minus 1 dimensional submanifold. And if n is greater or equal than 5, then you can write this boundary as a regular part union a singular part. And this regular part is a C1 beta n minus 1 dimensional submanifold. And this singular part is a closed subset of half-order dimension less or equal than n minus 5. Okay? So let me be honest. This, when we start here, this result was in the early 80s. This result is from a couple of months ago. So, and I'll tell you who did each one. So the contributions in the case when n equals to 2 are from the work of Alt-Caffarelli and Alt-Caffarelli-Friedman. Okay? That was included in the initial papers. In the case where n equals to 3, so there's the initial work of Alt-Caffarelli said the following thing. Their work said, forget the numbers, for not anything greater or equal than 3, the free boundary can be written as a regular set union a singular set. They knew that the regular set was a C1 beta n minus 1 submanifold, but with respect to the singular set, initially the only thing they knew was closed set of Hausdorff dimension of 0 Hausdorff dimension n minus 1. Okay? Okay. That was for the one phase. Then in the two phase, in particular, they did something, so I will tell you about the tools, but there was a comment that said if we were able to prove something, which I'll tell you later, what it was, then we will know that we have the same results that we had for the one phase problem. The thing is we're not able to do that at this point. Okay? So to work on the two phase, they needed a monotonicity formula that you will see in the next slide. And what happens in between this result and this result were two things. One of them is that work of Wegner, Koenig, and Pfeiffer, and also Hyman proved that what Alt-Caffarelli and Friedman had said, if we knew the following, then that was known, that was proven there. It had to do with how, had to do about eigenvalues of the Laplacian on the sphere, and also, let's say, when some inequalities became equalities and were achieved. Let me leave it there. And then, using that, and using a monotonicity formula by Wise, Caffarelli, Jerison, and Koenig were able to prove that the case n equals to 3, there were not singularities. And very recently, Jerison and Savin were able to prove, again, using Wise, plus a slightly different technique than here, but finding the right comparison again, that in the case n equals to 4, there are no singularities. Okay? Since, as Diego mentioned, I come from geometric measure theory, I want to make an analogy. This is very similar, for those of you who have looked at any GMT, this is very similar to what happens for minimizers of perimeter. And basically, there's a good reason, as we have seen, for these numbers to match. Okay? So what has happened also, you might be wondering, well, what do you expect? So the other thing, interesting thing that has happened is that Silva and Jerrison, a few years ago, constructed a minimizer in R7, which is a cone. Okay. So these amounts almost, it's the cousin of the Simons cone in GMT. And so the expectation is that for n equals to 5 and n equals to 6, this should be, there should be a big regular, there should be regular, but we're still not there. That's one of the nice open problems in this area. Okay, so this is everything that's known for the minimizing problem, and now I want to talk about the almost minimizers. So let me first introduce the first almost minimizers, and then I will do another analogy with geometric measure theory. Okay, so I need to first tell you who my class of functions are. So it's very similar. My class of function, the K class, is very similar, except that I'm assuming my function is greater or equal than 0 almost everywhere. And I look at the following thing. So I'm going to say that U in K plus is a kappa alpha almost minimizer for J plus. If for any ball that's included in here, J plus of XR, I'll tell you, look who that is. That's the integral over only the unit ball, on the little ball of the gradient of V squared plus the Q plus part, is bounded by 1 plus kappa R to the alpha J plus of XRV. So if you were a minimizer, this term will not be here. But you're not. So you're allowing a little error. Actually, now we have lots of other errors we can allow, but let me talk about this one. Okay, so when Almgren was looking, and we've heard about Almgren and his monotonicity formula, but Almgren was a big contributor to geometric measure theory. When he was looking at the regularity for minimizing surfaces, one of the things he noticed is that in one of the approaches he took, if rather than look at minimizing surfaces, he looked at these sets, which he called kappa alpha almost minimizers, he had up to order 1 the same type of regularity. Okay? So philosophically, when we started looking at these, and as I said in the last slide, I will tell you why, we started looking at these. When we started looking at these, our expectation was that up to first order, we should obtain the same things that were obtained for minimizers. Philosophically, that was the reason. Why philosophically this makes sense? Because in some sense, when you zoom in, an almost minimizer, what you see is a minimizer. Okay, so I'll make that more specific later. Okay, so these are the one-phase almost minimizers, and we define the two-phase almost minimizers in a very similar way. Here we have same thing, but now we consider the full function. Okay, so what's the big difference between a minimizer and an almost minimizer? A minimizer satisfies an equation. An almost minimizer doesn't satisfy an equation. Okay? There's no equation behind these things, but there's a variational aspect to it, which means you can compare it with other things, and you have an inequality. Okay, so what can we prove? So this was a work that we started a few years ago with Guy David, and here's what we were able to prove. We were able to prove that almost minimizers to J are continuous. So, and we have a modulus of continuity that I learned yesterday. It's called log lip. Okay. And so what this says is they're continuous all the way across. I don't have any more these things, so I will draw another picture in a minute. They're continuous and they have these. Okay. So this is almost Lipschitz, but not really. Okay. Let's go back. So what did they prove in the minimizing case, the positive part and the negative part were way smoother, in particular since the functions were harmonic, they were real analytic. So we also prove that they're nicer. So the minimizers are C1 beta in the positive part and C1 beta in the negative part. Okay. How do you prove these? So other times I do a proof. This time, unfortunately, I won't do a proof. But let me tell you how one goes about doing something like this. So we don't have an equation. Okay? What can we use? We can use comparison functions. So if you look at this work, the only thing we've done is find good comparison functions. We compare, and we use a couple of comparisons. They're mostly harmonic extensions. And we use iteration schemes. So basically, this requires comparison with harmonic functions and an iteration scheme. This requires the same thing, plus paying a little bit more of attention. Okay? On the other hand, this is not optimal. They had proven that there were Lipschitz across. We want to prove that there are Lipschitz across. I mean, you know, Lipschitz is, since what we're trying to prove is that up to first order is similar, we have to prove Lipschitz. Okay, so what they had is that they were Lipschitz. Let me remind you how they did it. I'm not going to remind you the proof. I'm going to give you the three main ingredients of the proof. The ingredients were U plus and U minus are subharmonic in omega. And the way I read the papers, the key feature to that was that the Laplacian of U plus and U minus are non-negative read-on measures. That was the key point. They're harmonic in the positive and negative part. And then in the two-phase case, they needed a monotonicity formula, which I will call from now on the ACF monotonicity formula. And here is what it says. It says that if you look at this quantity, 1 over r squared, this number, times 1 over r squared, the same thing for the negative part, this is an increasing function of r. Okay? The proof of this is a beautiful analysis of how the relationship of the eigenvalues of the Laplacian on spherical sets, on spherical caps, and the relationship between them. Okay. Okay, so the point is, so what do we do? So first notice that we don't have subharmonic functions, we don't have harmonic functions, and apparently we don't have a monotonicity formula. But we prove exactly the same thing, of course not the same way. How do you prove that? So we prove almost minimizers are Lipschitz across. Okay? What are the tools? If you want to prove that something is Lipschitz, what do you need to prove? You need to prove that the gradient is bounded. The pointwise gradient here doesn't make sense. What do I need to prove? We need to prove that the average of the gradient squared, I like squares, is bounded. Okay, so what do we do? How do we prove that? We use we look at the interplay of three quantities. For those of you who have looked at this type of problem, you recognize this is an important quantity. It really measures the average, and 1 over r, it tells you whether at the point x in the free boundary you have a degenerate solution or not. For the two-phase, we need to look also, because it's not the same thing, to integrate these as to integrate these. To the one phase, since the function solution is positive, these are the same. And now we look at the key point. This is my gradient. So to prove that the function is Lipschitz, I need to prove that this is bounded. In fact, to prove the previous results, the regularity results, we had proven estimates on this guy. Okay, so that's my goal. And so for the one-phase problem, the proof goes by using the relationship by very carefully looking at the interplay between this guy and this guy. And the regularity result we already have. Now, in the two-phase, we need an almost monotonicity formula. And as you'll see, this initially controls the oscillation of this function phi of r in small intervals. Since I know some of you like monotonicity formulas, and these might be useful. Let me tell you what our almost monotonicity formula looked like. So it was exactly the same, basically. If you use an almost minimizer for the two-phase problem, there exists a small delta here, depends on alpha and on n, slash that at small scales, okay, if you don't have that this is a decrease, this is not an increasing function, but it's almost an increasing function. There's a little error, okay? And here is the same functional that they had. And so we combine these tools to prove that the almost minimizers are Lipschitz. Okay. So now we have proved the regularity of the function. We want to prove the regularity of the free boundary. Okay. Before we go, if you look at the results, the key point, a very important part, was that non-degeneracy. Remember when I said a super important part was the fact that the value of the function u here for the minimizer was comparable to this distance. If we want to accomplish anything else, we needed to prove that. So that's our next step. And I'm going to switch to the one phase. We have results for the two phase. In particular, this one holds for the two phase also. But at some point, the results are not the same. And rather than say up to here, this is a good place to switch to the one phase problem. So if we're looking at the one phase, Q is continuous and bounded below. And continuous is not optimal. We need less, but it's easier. Then the following thing happens. This average is positive. And in particular, what it tells us is, and now I'm going to change my picture for my almost minimizer. So I don't have positive. But what this says is that if this is x naught, and let me put r naught here, basically what this is telling me is that every time I take a point here, the value of is comparable to this one. Okay? So remember, u of x over delta of x. This symbol means it's comparable, is bounded above and below by constants that don't depend on anything other than allowable things. Okay. And now, if you are from GMT and you want to look at the free boundary, the natural thing to do is do a blow-up analysis and try to see what goes on. So let's see what happens. So in order to understand the structure of the free boundary, we look at the tangent objects. We blow up. You blow up the function. What does it mean to blow up? Well, let me explain by hand, since clearly what's going to happen is I'm going to tell you this is lovely, but it doesn't work, so I'm not going to waste time going. So what does it mean to blow up? You want to understand the infinitesimal structure of gamma of u. Think that you're teaching your calculus class, for those of you who teach calculus classes, and you're teaching your students whether you want to convey the idea of having a tangent, okay, on the graph of a function. What does a current student do? They plot on their calculator. They do like these. They open, enlarge, 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 and they see a line, okay? So looking at the tangent object means you do exactly the same thing. You look at the function, you enlarge it, and see what happens. Here we look at the function, we see what happens. We look at the free boundary, we see what happens. The non-degeneracy and Lipschitz tell us that when we do these, we get a nice function. And GMT tells you that you get a set, a nice, possibly nice set. Okay, so we did these. What do we know? So a very, very raw philosophical argument. What do you do when you have a problem of this type? You said, I blow up at almost every point I get a nice thing. Therefore, I end up getting regularity in a big set and a set of small measure. Okay? So, but for that, you need to understand the blow-up. So what do we know about the blow-ups? When we blow up, and let's just think of the tangents, all tangents are global minimizers, or either the Alt-Caffarelli or the Alt-Caffarelli and Friedman functionals with constants with constant function q plus and q minus. So you might say that's great because we know, and let's assume you're in dimension 3 or 4. Okay, all my blow-ups are planes. Great. So there's one little issue. Well, so first issue, they're not understood. Let's assume we're in dimension 4, they're well understood. Here is the catch. We don't know. So I blow up, and I do a blow up in dimension 4, and I land in this plane. You do a different blow up, and you land in this plane. And I don't have any mechanism. This blow up thing doesn't tell me that I have a unique limit. Okay? And so I have a problem. And I have a very serious problem. Okay, so we needed to deal with this. And the truth is, this was our first attempt. And actually, we can go further along, but we were truly stuck. We didn't have a mechanism to say, I have a unique blow-up. And we didn't have a mechanism to say, even if I've discovered that at this point here I have a unique blow-up, we didn't have a mechanism that allow us to say, at almost every point I have a unique blow-up, because we don't have a measure. Okay? We didn't have a measure at this point. Think of my story. I haven't told you that for an almost minimizer, I have a measure. On the other hand, Alt-Caffarelli-Friedman had measures because they have subharmonic functions. The Laplacian of u plus was supported on these, and it had very nice properties. So I go back to where I come from, which is GMT, and I wanted a measure. More than anything, to address this problem, I wanted to construct a measure on this gamma of u that will tell me something. Okay? So the blow-up argument won't do it for me. So we changed gears. And this is where maths came in. So the first thing we did is, so we're looking at almost minimizers. And the first thing we did is we proved that the positive part, this thing here, is an NTA domain. So NTA means non-tangentially accessible. If you are familiar with this notion, it's great. If you are not, please ignore it for a little bit. I'll remind you, David to some extent mentioned some of it, but it's a good enough domain that allows you to do some things. Here, the proof of this, we did it by ourselves and then realized that we could have used some of the ideas of the Silva and Jerison to make our proof, shorten our proof. Okay, so it's basic. And now, remember, I told you, I am looking for the measure, and having an NTA domain allow me to construct a measure. Okay, so you see there's a little asterisk here. Means that don't worry if you don't understand. I'm going to draw a few pictures later, and I'm going to go over these. What this means is that that for x naught and the free boundary, as long as I look at a ball that's inside my domain, I can construct an Alford's regular measure, which is supported here. What is an Alford's regular measure? It's a measure for which the ball of radius r grows like r to the n minus 1. Okay? We're going to talk about these anymore, but if you want, this is a very, very nice looking radon measure. And once I have that, and I have non-tangentially accessible, we can prove uniform rectifiability locally. What on earth is that? Okay, so it's better than rectifiability because there's the word uniform in front. I mean, you know, but no, what it really means is that at each point, every time you look at a ball, not only do you know that this is a countable union of Lipschitz images, you know that 80% of the set is the Lipschitz image of somebody. Okay? So it's a quantified version of rectifiability. Why were we happy? Well, yes, well, it's a nice result, whatever, but in particular, if you're uniformly rectifiable, you're rectifiable, and therefore, you have unique tangent objects. Suddenly, we have constructed that measure, and we have constructed the unique tangent object at almost every point. We're in business, Okay? I want to point out that even for minimizers, this had not been done. So in particular, we have that this is a set of local IMPA net perimeter. But as I said, this was for us the key point. Okay? We have these unique tangent points almost, or unique tangent objects almost everywhere. Okay. So let me go for a minute to. So I would like to spend a little bit of time. This is a very dense overhead. These I'm not going to mention. I would like to talk a little bit about these. And the reason I want is because, you know, when we do free boundaries, sometimes to try to prove things, we use a set of tools. We often blow up. And this is kind of a different one. If you could construct a measure on your singular set, there's many things that you can do. It's not easy, but there is another example when Fang Hualin years ago was looking at sequences as he was looking at sequences of, well, he was looking at the singular set of stationary, there were harmonic maps which were satisfy the monotonicity formula, and he wanted to prove something about the singular set. The reason he was able to do this is because he was able to build a measure on the singular set. So it's an important tool, maybe not easy to implement, but sometimes it works, okay? So let me tell you how it works, why it works. Okay, so now it's time to draw my picture bigger. So here it is. Sorry. Now this thing here is going to be my x0 and my r0, 4r0. I am trying to prove something about this. This is the positive part. And they don't satisfy an equation. I need an intermediate function. Here is my intermediate function. As most of you might have guessed, I'm going to have to use harmonic functions. Okay? So what we're going to do is the following. I am going to consider, the first thing to prove is that this is a good comparison, but we can do that. We are going to look at the harmonic function. So I look at this set, and we prove that there exists a small r0, that if we look at this harmonic function here, and now this is really rho 0. There's a relationship between r0 and rho 0, but it's not important at this point. If we look at the harmonic extension on the boundary of this thing, so I'm looking at the harmonic extension of u here. Okay, so now this is a good function. It's harmonic. It's not an almost minimizer, but it's harmonic. You know, you cannot have everything in life. And then look at what it happens to this one. Then h, if I look in a smaller ball, maybe I should remove. Now you see who h is. I'm going to actually, sorry about that. It's very bad board technique, but Laplacian of h equals 0, and this little piece here, and h equals 0 on the boundary. And what happens is if I go to a slightly smaller ball, so this thing here is theta rho 0, then I have this relationship. H of x is comparable with u of x, and I can make it as close as I want, okay? So these reads for every epsilon, I can choose an r0 such that the following thing happens. Why am I happy? Well, the reason I'm happy is that this tells me that this harmonic function h is Lipschitz and is non-degenerate. So for everybody here, I have the following property. H of x over the distance of x to the boundary is comparable to 1. And now I have a harmonic function. I know it's defined in a little piece, but it doesn't matter. I have a harmonic function which at the boundary grows like the distance to the boundary. Okay? Now I also do some PDEs, and for us that was very happy because that allows me to construct this measure. Okay? So if you have ever looked at elliptic functions on Lipschitz domains or on non-tangentially accessible domains. You are familiar with an estimate that's called Caffarelli-Friedman salsa that allows you to compare the Green's function that tells you that, morally speaking, the derivative of the Green's function corresponds to the Poisson kernel. All of you know that that's the case on a smooth domain, but morally speaking is the same. So that's what allows us to construct our measure. Let me explain how. So this is how you construct this measure. So we have our function h, and now here is what happens. I look at, this is 4R0. I take a point A0, which is a distance, it's not necessarily the same 0 here, which is a distance roughly R0 from the boundary, so really exactly there. I look at the harmonic measure with pole here. What's the harmonic measure? The harmonic measure is simply the probability. So the harmonic measure is supported on the boundary of this domain, and is the probability that a random walk starting here first will hit the boundary at a given set. And that measure, okay, that measure satisfies this property. Okay? So, if you have never seen any of what I'm about to say, please take a 2-minute break. If you have, let me try to convey a very rough idea of what we do. We have a harmonic function with linear growth at the boundary, exactly linear growth. It tells us that the Green's function in this little ball grows exactly the same way. This is a non-tangentially accessible domain. I can relate how the Green's function on this domain, how this relates to this one over here on this little piece. And once I have the control of the Green's function at this point, so we prove that the Green's function at this point in this little neighborhood behaves like that, then you have control of the harmonic measure. Okay? So this is a number of results that come from, I guess, harmonic analysis and intersection with PDEs. Okay? So, but notice why we have the measured. We have that this measured is radon, and in particular the fact that we have that this, so this condition here means that it's alphors regular. So now the fact that we had an NTA domain whose boundary had an alphors regular measure allows us to say that it was uniformly rectifiable. That's how we got that result. Okay? So now I said, morally speaking, you know, if I can control, I have this on this little ball, I can keep on going. But in fact, we needed an iteration scheme. So how did we prove, for example, how did we prove this? It required an iteration scheme. And it required us, because this harmonic function that we built is not, we don't have the estimate to start with. So rather, the reason why I blow up the n-work is because what we need is we need to do a multi-scale analysis, okay? We compare with a given harmonic function first, with one later. And so we do an iteration scheme, and the almost minimizing property allows us to compare different ones of these functions h that we constructed associated with a given radius. We use the property of non-negative harmonic functions on NTA domains, as I described. And then we use the result of Caffarelli-Friedman, and salsa on NTA domains to obtain the result. Okay? So, but that was very good. So finally, we had our tangent objects. And so when the Q is continuous, that's the best that we could expect to have uniform rectifiability. I don't know if, okay. But as I said, what we wanted to do was to do exactly what Almgren had done, and was show that up to first order we have the same thing. So what else can we say about the free boundary if we assume higher regularity of Q plus and Q minus? So let me tell you the higher regularity. So what have I done here? Please notice I am only talking for now about J plus, and here I really am only talking about J plus. And I am assuming that Q plus is whole or continuous, and is of course non-degenerate. And then we can write gamma of U as a regular part times a singular part, but of course it's not as nice as, well, not yet. The regular part is a C1 beta n minus 1 dimensional submanifold, is relatively open subset, and sorry, and the singular set is a closed set of n minus 1 Hausdorff measure 0. Okay? And of course, I'm going to show you some of these. So what do we need? We need an almost monotonicity formula, but now of the Wise type. And we also need a flatness improvement lemma. And for those of you who are familiar with Alt-Caffarelli, this makes sense. Of course, we don't have an equation, so what on earth am I talking about? Don't worry, I'll get there. Okay. Let me tell you so we have several Wise Wise type monotonicity formulas. Just let me show you one. So we look for if U is an almost minimizer of J, and Q plus and Q minus are C alpha, and we look at these functional. So if you are familiar with Wise, this is what Wise looks at. Wise has two versions, this one minus these, and this one minus something slightly different. We have an almost monotonicity for both of them. And what we're able to prove is that omega r minus omega s is bounded below by a positive quantity. This positive quantity, of course, plays a crucial role in the work of Wise. I'm here taking my free boundary point to be 0 just because it's simpler. And I have a little error, but the error is of order r to the alpha. Okay? So this is the first ingredient. Now, let me tell you what it means to be flat. What's a flat point? Okay? So I said the two ingredients was Wise monotonicity type formula, almost monotonicity, and a flatness result. Okay? So I'm going to draw flatness, then we'll define flatness. We're going to say that a point x naught is flat at a radius r naught if the following thing happens. There exists a vector, E, unit vector, such that when you, sorry, I don't know if I have already put everything or not. Yes. So we say that U is flat, and I'm going to leave it in B x naught r naught if the following picture holds. When you look at here, you know that U is positive here, but not only that, you know that U grows linearly, and here U is 0. So let me put it, let me put it there, and then you'll see. U of x here is bigger than Q plus of x naught. X minus E, x minus x naught E, and then a little error, and this isn't the case. Oh, and sorry, there is a typo. That's the fear. Okay. There's a serious issue with being broadcast live. Now your errors are broadcast live. Okay, you need to add a little bit. But basically, it's telling you that above here, U is positive and linear, and here it is 0. Okay? So it's the same condition that Alt-Caffarelli had at the beginning. They had other conditions. We cannot talk, the other conditions don't hold for us. That's why they're not there. But so we say that you're flat in this direction. And of course, the flatness improvement lemma says what you really wanted to say, which is that if you are flat enough at a given radius, which depends on, and then you look, you can find a smaller radius here, such that when you enlarge here, what you are seeing is possibly in a different direction, a flatter picture. Okay? That's the content of this slide. Okay? So it tells you that if you start flat, then you can improve your flatness by a fixed amount on a fixed radius. Okay? So how do we do these? Once again, it's a multi-scale analysis, and we do use Alt-Caffarelli, but not, so the ideas in Alt-Caffarelli, but not applied to the function u, because the function u doesn't work, but the intermediate functions h of r. What happens is that at each stage, we use a different function h of r, and we need to keep track of what's going on. Okay? And while the function u doesn't satisfy any condition on the gradient, the function h does. Okay, so that's how we make it work. Okay, so now let me tell you what else what are the things that are left that we are thinking about, and let me tell you why we started doing this. Okay, because so what's left? So sorry, I should have emphasized. Well, this yields the C1 alpha regularity, C1 beta regularity, where we're looking for the free boundary. So what we are looking for now, we need to understand the two-phase problem. How was it done in Alt-Caffarelli-Friedman? Really, that's one of the spots where this theory goes to the viscosity solutions and you get the regularity. And unfortunately, that doesn't work for us. Okay? So what we need to do, the way we need to approach this is more like Alt-Caffarelli approach their problem. And so we are looking into implementing an improvement, a flatness improvement lemma, more along the lines of what De Silva, Ferrari, and Salsa have done in order to obtain the thing we need. So that's a way to bypass the viscosity solutions. You can say we don't understand them well, but in this case, they're not adapted. Okay, they're not well adapted. Okay. The size of the singular set. As you saw, while in the minimizing case, there's beautiful reduction of dimension. In this case, we don't have the dimension reduction. We expect to be able to get it. We need more work is needed. So this is relatively recent, so I don't, okay? So that's the next thing we would like to say. And now let me tell you why we started. Okay, so what happened was the following. When Manolis arrived, so Manolis had done his PhD with Yanis, he had spent some time with Liz, he had looked at other free boundary problems, thin obstacle problem. He came and I said, oh, why don't you learn this? So what you should do is look at Alt-Caffarelli, put in here a metric, a Riemannian metric, which is C0 alpha, and let's do exactly the same thing. And what I was hoping this was a project where Manolis was going to read, Alt-Caffarelli was going to come and was going to say, oh, in this case, you do this. And it was a nice, that's what I thought. It was a nice homework. And then we got stuck. Okay, we did something else. And Manolis learned something else. And we left it there. And what we realized is, okay, well, I cannot do this directly. I wanted a direct proof. I didn't want a viscosity solution proof. I wanted a direct proof. And what we started, once you're stuck, you start playing. And so I froze the coefficient. And I said, well, it's almost like if I had this with an error. And that's what led to the almost minimizers. The point is that now we're looking at the almost minimizers for this case. And at least up to now, we're able to prove, forget that in one phase, okay, they're Lipschitz, and we're in the process of looking at their free boundaries also. But so our goal when we started these was to study the regularity of the minimizers for this one and the corresponding free boundaries. Okay. Thank you very much.
Thanks, Tatiana, for the beautiful talk. Is there any questions or comments? Let me